This video is the first video in a two-part series covering section 6.4, Working with Taylor series, out of the OpenStax Calculus book, Volume 2. In this first video, we're going to discuss what binomial series are and how to use them as an example of a power series. In order to do this, we first need to understand what a binomial series is. Most of the rest of the learning objectives for this section will be covered in the second video. Binomial series are something that is relatively new to most students because we never have enough time in college algebra to cover it. Let's take a simple example. When we think about a Maclaurin series for a function based on a binomial, where the binomial is raised to a power p for real numbers p, this is known as a binomial series. So a binomial series, like many of the others, is just another example of a Taylor series, which is also, of course, a power series. In the simplest case, p will be a whole number, 0, 1, 2, 3, 4, 5, and so on. Now, of course, if we had 1 plus x raised to the 0th power, that would be 1. I wouldn't really call that very powerful. In typical, we have powers that are greater than 1. However, we can also have powers that are between 0 and 1. When we have powers that are not whole numbers, we don't end up with finite polynomials. Finite polynomials are reserved for powers of binomials where the power itself is a whole number. These give us a finite polynomial. Here in the center of the page, you will see the binomial expansion of the first four powers of 1 plus x. 1 plus x to the 0th is, of course, 1. 1 plus x to the first is, of course, 1 plus x. 1 plus x, that binomial being squared, will give you 1 plus 2x plus x squared. But you're probably used to seeing it more like x squared plus 2x plus 1. If you continue the expansion, you will get the multiplied out polynomial. Notice that in all 5 of these cases, the power on the binomial is a whole number, and we end up with a finite polynomial as the result. The results on the right, where they're fully multiplied out, are called the binomial expansions. The constants in front of each term, for example, in the expansion of 1 plus x to the 4th power, the coefficients 1, 4, 6, 4, and 1 are known as binomial coefficients. In general, for any non-negative integer p, the binomial coefficients of x to some power in the binomial expansion of 1 plus x to the p is given by the notation you see here in the center. You're probably not familiar with the notation on the left. On the right, you should now be familiar with the factorial notation after having done the ratio test so many times. If you've studied probability, you may well have seen this notation on the left. This is what's often called the number of combinations of p different objects taken k at a time. Sometimes, and usually for a probability class or a statistics class, this is denoted with an uppercase letter C followed by parentheses with n comma r inside of it. The n and the r represent the total number of objects, which of course is n, and the number of objects that you're choosing at that one particular moment, which is r. R is always a subset of n. For example, in a class of 30 students, I may ask myself, how many different ways can I group my 30 students, that's my total, or n, into groups of 5? The 5 would represent the r. If we use the notation that you see here above it, then the p would again take the place of the total number of students, and the k would take the place of the number of students you're pulling out at that one particular time. So in the example I gave, p would represent the 30 students in the class, k would represent the number of groups of 5 students each that I can make out of that group of 30. It turns out that the formula for creating that number of combinations is given by this formula. In our case, that would be 30 factorial divided by 5 factorial times the quantity 30 minus 5, which is 25, factorial. It turns out that there are a whopping large number of different combinations that I can make of 5 students taken out of a group of a total of 30. Now, your book uses N and R, but unfortunately, it uses them in the reverse order from the normal fashion for combinations. And on the off chance that you're headed for statistics with calculus at some point, I don't want to confuse you. So instead, I'm going to use K and P in this section of the textbook. But again, what this means is that I have P number of total things, and I'm choosing K at a time. This will only apply, of course, if P is a whole number, and that's what we mean when we talk about combinations. For a binomial series, however, we allow P to basically be any real number you want, and this will give you any particular expansion. We'll use this formula even when P and K no longer make sense in the sense of taking a set number of objects and grouping them out of the total number of objects. This formula is the same thing that you get when you look at Pascal's triangle. Most of you have probably never seen Pascal's triangle, or you've only seen it in passing. You've never really had to use it. Pascal's triangle is relatively easy to write down. We'll cover it in just a moment. I do want you to be aware that some of these things may well be on your calculator. The N choose R is on most calculators. On a graphing calculator, you want to hit the math key. You generally will have 4 options across the top of the screen: math, num for numbers, CPX, and PRB for probability. Since this is a formula that comes up in probability, you'll use the right cursor key to get to probability. Scroll down to option 2 or enter the option 2. Permutations is option 2, but actually what we want is combinations, which I believe is usually number 3. On the sharp right view, which many of my students use in class, you'll find this in the second function color above one of the number keys. Different ones might have it in different places, but in general, you'll find permutations, which we will not be using for binomial series, above the 5 key, and combinations, which we will be using, above the 6 key. To get there, hit the colored key for the second function, and then the number where you see it. You generally have to have already entered the number for the total, in other words, the N, or in our case, the P. So to get P choose K, you would hit, for example, 30, then you would hit the second function button, and then you would hit the 6 key, and then you would enter 5 to get the number of combinations of 5 students at a time taken from a group of a total of 30 students. You will have to keep in mind that these involve factorials, and factorials grow faster than just about any other kind of function we study, except power functions. They grow extremely quickly. Sometimes calculators can't handle what you're doing, so don't be surprised if you get an error message. It may not mean that the answer doesn't exist, and it may not mean you've done anything wrong. It just may be too large for that calculator. You may have to calculate that one by hand using the formula that you see here in the center. Let's talk for a minute about Pascal's triangle, which I've said many of you may have only seen in passing. Keep in mind that while we give Pascal the credit for it as a French mathematician, since he did a lot of the early work for statistics and probability, mostly because he liked to gamble and wanted to know the odds of whether or not he would win, it actually was discovered centuries before in China. It is also called Yanqui's triangle. It has many, many applications in mathematics. This is just one of them. How do you produce Pascal's triangle or Yang-Hui's triangle? You start with the 1 and you're going to build a triangle shape or a pyramid. The 1 goes at the top at the pinnacle or the top of the pyramid. In the second row below it, you will also put 2 1s. The 1s have to be offset from the 1 above them, meaning there should be blank space between them directly below the 1 at the pinnacle. When you continue, notice that every row begins with a 1 and every row ends with a 1. To find the numbers in between the first and the last, look at the row above it, add the 2 numbers on either side of that open space, and put them here. 1 plus 1 is 2, so we get a 2 here. Here you'll see a 1 plus 3 gives me 4, 3 plus 3 gives me 6, 3 plus 1 gives me 4, and I end that row with a 1. In this way, you can build as many rows as you need out of Pascal's triangle. Now you may be wondering, what the heck does that have to do with multiplying together binomials and getting expansions? Notice here that in the power 4, which is actually the 5th one produced, if we start counting at 0, the coefficients are 1, 4, 6, 4, 1. Again, 1, 4, 6, 4, 1. Keep those numbers in your head and let's go back to Pascal's triangle. Do you see here that we have in the 5th row down, which we call row 4 because we count beginning at 0, 1, 4, 6, 4, 1? You got it. The numbers that are produced in this triangle represent the coefficients of the binomial expansion when the power on the binomial is a whole number. You must remember to start with row 0. And in fact, if we are counting across a row, we would call the first one the 0th element, the second number the first element, and so on. Each row of Pascal's triangle counts as a subset of a set. It's an n-element set, and that gives us the combinations. You'll see here in this schematic that they have represented Pascal's triangle with the actual combinations that you get. So for example, in this row here, this particular number represents the different numbers of groups of 3 that you can make out of a group of 5 total students. Let's see if we can find it in Pascal's triangle to the left. Again, we're looking for 5, choose 3. Out of 5 students total, how many different groups of 3 can I take where I don't care what the order is that the 3 are put in? This is row 0, row 1, row 2, row 3, row 4, row 5. Do you notice that the second one actually gives you the number of the row? That's always going to be the case. It works here too. This doesn't have a second number, so it's row 0. This second number is 1, 2, 3, 4, 5, and so on. So again, 1, 2, 3, 4, 5, 6. I need the 6th row down, so I go till I find the 6th one down. 1, 2, 3, 4, 5, 6. Notice that this is actually considered row 5 because we begin counting with 0. 5, choose 3 is the 0th, 1st, 2nd, 3rd one across, and that will give us, coming out of this row, 0th, 1st, 2nd, 3rd. There are 10 different ways that I can group just 5 people into groups of 3. We don't have enough to figure out how many different groups of 5 I can make out of 30, but I can tell you it is a whoppingly large number. You'll see here where they have lined up the exponents in a column to correspond with the rows of Pascal's triangle. And next to it, they've highlighted in red the coefficients of the binomial expansion so that you can see the relationship. Notice that the exponents here are lagging behind. Now, let's take a look at our next step. The exponents are a little bit offset from the rows. This is row 0 with exponent 1 corresponding to the 1. This is row 1 corresponding to the first power, which has its coefficients here. This is row 2. In fact, this is row 5. It is not being raised to the 6th power, it's being raised to the 5th. Here is its expansion here with 1, 5, 10, 10, 5, 1. You'll also notice, because of the way that Pascal's triangle is built, that they are symmetric as they move across. Now we're going to suppose that P is not just any whole number. We're going to suppose that P is any real number at all, and for convenience sake, we're going to eliminate the whole numbers. We know that if they're whole numbers, it will give us a finite polynomial expansion. But what if it is not a whole number? What happens then? If it's not a whole number, we will allow it to be positive or negative, a fraction, whatever. In this case, the 1 plus x raised to the p power will not be able to be written as a finite polynomial. That's only in the case that it's a whole number. However, we can find a power series expansion for this binomial raised to that non-whole number power, provided we center it at 0. The coefficients in the binomial expansion series will be given by this formula here. You'll notice again that this is the kth derivative of the function at 0 divided by k factorial times p minus 1, p minus 2, all the way down to p minus k plus 1. The reason is, as you continue to take the derivative of the function over and over again, the p comes to the front, leaving on top a new power p minus 1. The next time you take the derivative, the p minus 1 comes to the front, then the p minus 2. If you take the kth derivative, you get coming to the front the last one, which is the one right before p minus k. That would be p minus k plus 1 more. This means that we can write the binomial series expansion for 1 plus x raised to the p power in this format here. Now, this is a pretty long and expanded formula to remember. We're probably not going to be able to remember it, so instead we have a way of shortening it. We use this formula or this notation in parentheses with the p written directly above the k to represent this coefficient here consisting of p times p minus 1 times p minus 2 times all the way down to p minus k plus 1 divided by k factorial. Those are the coefficients that you'll find in front of the x to the kth terms. Now, let's continue and move on to see how we can apply this. Realize that once you get the power series written, and a binomial series is a power series, then you will probably need to use the ratio test in order to find the interval of convergence. Just like you've been doing before with Taylor and Maclaurin series, you will have to test the endpoints separately. In the two blue boxes in the center of the page, you'll find the official definition for the binomial series. For any real number r, which is what your book is using, while I will use instead p, the Maclaurin series for the function 1 plus x raised to the r is the binomial series. It will converge to that function provided the absolute value of x is less than 1, as is typical for most power series. Instead of using the r and the n as the book has done, I will again instead stick with p and k. I find it simpler rather than trying to remember whether I'm looking at probability and statistics n and r or calculus 2 n and r. So for me, this will read, for any real number p, The Maclaurin series for f of x equal to 1 plus x raised to the p power is the binomial series. It will converge to the function provided that the value of the absolute value of x is less than 1. And I will instead write that 1 plus x to the p has to be equal to, and let me take this part out and write instead p choose k times x to the n. Since this notation is almost certainly unfamiliar to most of you, or perhaps all of you, let's just practice a little bit working with the formula for p choose k in order to just work out what the coefficients are. I've used a variety of different p values, a negative integer, a positive fraction, and a negative fraction. Keep in mind that none of these have any real sense in the real world. I can't take groups of 2 out of groups of -3 people. That doesn't make any sense at all. However, the formula is the same as the one used in probability and statistics for combinations. If I want to find -3 choose 2, I will need to write it down using the formula. Now, if I'm going to do that, the numerator, of course, is p factorial over k factorial, p minus k factorial. There is a shortcut to this, however. Let's look up here again and see what the shortcut was. The shortcut, of course, is to start at whatever the value you're given, multiply by all the ones in front of it until you reach the upper value p minus the lower value k plus 1, and then stop. So coming down here, rather than use the formula, I'm instead going to use the other formula, which is that this must start with -3, and it must continue until it will get to the following. It continues to p minus k plus 1. P minus k plus 1 would be -3 minus 2 plus 1. -3 minus 2 plus 1 would turn out to be a -4. What is the number after -3 when I subtract 1? Bingo, it is -4. I take that value and I divide it by k factorial. In this case, our k is 2, so I divide by 2 factorial. Now notice that in the formula for p choose k, the bottom number here will always be a whole number, since it will be the value in the summation notation itself. It also always tells me exactly how many factors should be in the numerator. If this is a 2, I should have 2 numbers together multiplied in the numerator, and the denominator should be 2 factorial. Would I have gotten the same thing using the formula p factorial over k factorial times p minus k, the quantity factorial? Let's check it out and see. If I use that formula, then I need to plug in the values of p and k and work out the formulas with the factorials. P in this case is -3. Now that's a bit of a problem since we've never had a negative in a factorial before. However, we'll use our idea of what a factorial does to see if we can simplify it. Since k is 2, that gives us 2 factorial. P minus k, on the other hand, would be -3 minus 2 quantity factorial. Using our knowledge of what factorials do, remember that factorials will take the number and multiply it by each number in front of it. In other words, by subtracting 1 each time. In that sense, what I need to do is rewrite the one in the numerator, the -3 factorial, in such a way that I can reach the one in the denominator, the -5 factorial. If I do that, I will get -3 times the integer immediately to its left by subtracting 1, which is -4, times -5 factorial. When I divide, I have 2 factorial in the denominator times the other -5 factorial. That means that the two -5 factorials will cancel, and I'm left with exactly the same formula that I got up here using the opposite formula. Let me write the opposite formula for you at the top. This P choose K can also be written as P times P minus 1 times P minus 2 all the way down to P minus K plus 1 all divided by K factorial. You can use whichever formula you prefer, but in general, I tend to use the second one, but more as a guide, since I already know that the bottom number tells me I need 2 factors, and the first factor is always whatever the number is in the top. So this tells me start at -3 and subtract 1 from it, multiplying each factor together until I have 2 of them, and divide by 2 factorial. Let's take those steps and now apply it to 1/2 choose 3. If I'm looking at 1/2 choose 3 and I want to apply the technique I just mentioned, I can write it in the following way. I'm going to start with my first factor being 1/2, and the 3 means I need 3 factors in the numerator. In the denominator, I need a 3 factorial and 3 factorial in the denominator. Let's see if we can do that. Each time I multiply by a factor, it's got to be the previous factor minus 1. If I take 1/2 and subtract 1, the next one I get is minus 1/2. The next factor I would get is -1/2 minus 1, which is -3/2. That's 3 factors, so I stop. And I'm going to divide this by 3 factorial. Again, let's see if it worked using the formula. Is -3/2 P minus K plus 1? If I do P, which is 1/2, minus K, which is 3, and add back 1, this is the same as 1/2 minus 2, which is in fact -3/2. The fact that the last factor here matches P minus K plus 1 tells me I've almost certainly set it up correctly. Let's do the last one now. How would we work with -1/2 choose 4? If I'm looking at -1/2 choose 4, then I will need to write it in the parentheses. I will need 4 factors in the numerator, with the first factor being -1/2. If I subtract 1 from -1/2, I get -3/2. Subtracting 1 again would lead me to -5/2. Subtracting 1 again is -7/2. I stop there because the denominator number is 4. Well, not really denominator, let's call it bottom number, is 4, which is the K value, and I have 4 factors now for the numerator. I need to remember to divide by 4 factorial. To check it, you can compute P minus K plus 1, which is a -1/2 minus 4 plus 1. Minus 4 plus 1 would give me -3. If I take -1/2 and subtract 3, I would end up with, what would I get? -7/2. There you go. They match. Let's move on and look at the next example. In example 2, we want to find the binomial series for the function, the square root of quantity 1 plus x, which is centered at 0. Then we'll use that binomial series to approximate the square root of 1.24 to 3 decimal places. We will assume that the series for f does converge to f on the interval of convergence, which in fact it actually does. Remember from our previous video that the only way to know for sure that the series for a function converges to the function is to prove that the remainder goes to 0. In general, on the exams, I will not expect you to prove this. I will instead tell you to assume that the series for the function does converge to the function on the interval of convergence. Assuming that, how can we take what we've learned and find a binomial series representation for the function the square root of 1 plus x? First, we need to write it in a binomial form. To write it in a binomial form means that we need to find a power p being applied to 1 plus x. We need to know what p is so we can compute p choose k. In this case, our p is going to be the 1/2 power. If I write the square root of 1 plus x, I could convert it to its rational exponent form by writing it as the quantity 1 plus x to the 1/2 power. That makes p be 1/2. In order to compute this, I need to find the coefficients. A simple way to do it, and we'll compute, say, the first 5, would be first 1/2 0. Now this is one I did not have up above, but by convention and by definition, we define any of these choice computations for the coefficient to be 1 if k is 0. You cannot use the formula to develop this one. Instead, you will just simply know that if the bottom number is a 0, it's defined to be 1. That gives us the first of the 5 we want to compute. How about the next one? If you're writing a series representation and starting with n equal to 0, your next n value would be 1. So we'll need to compute 1/2 choose 1. To compute 1/2 choose 1, I start with the upper number in the numerator as a factor. The denominator is going to consist of the bottom number with a factorial. The bottom number also tells me I need one factor in the numerator, which I have, which means I just get 1/2. The second time I compute it, I have 1/2 choose 2. K has gone from 0 to 1 and now 2. To compute this one, I can simply remember that this must be 1/2, subtract 1 from the 1/2 to get minus 1/2, which gives me 2 factors to match the 2 in the denominator, or rather on the bottom, and then divide by 2 factorial. Again, if you want, you can compute p minus k plus 1 to ensure that you're setting it up correctly. 1/2 minus 2 plus 1 back is negative 1/2. For the next one, we will find 1/2 choose 3. For 1/2 choose 3, due to the 3 in the bottom number, we will need 3 factors in the numerator and 3 factorial in the denominator. This will give me 1/2 times negative 1/2 times negative 3/2, all divided by 3 factorial. This will simply produce a constant. When I compute p minus k plus 1 to check my work, I get 1/2 minus 3 plus 1, which is 1/2 minus 2, which is negative 3/2. In order to find the true value, we do want to go ahead and multiply these out. If I'm going to multiply them out, have you noticed that there is a pattern to this? When I get to the 1/2 and I go to the next one, notice that I have a 1/2 in the numerator here times another factor, negative 1/2. When I move to the next one, I have the previous factors in the numerator, but I also have another factor, negative 3/2. In the denominator, instead of 2 factorial, I have 3 factorial. There is a pattern there as well, which you are welcome to use to generate from one to the next to the next. Let's generate one more coefficient. We'll do 1/2 choose 4. I'll start with 1/2, then -1/2, then -3/2, and then -5/2, stopping when I have 4 factors in the numerator to match the 4 in the bottom. Then the denominator becomes 4 factorial. Let's see if we can now compute what these constants are. For the first one, we're done. It's just 1. We can go ahead and outline that in red so we can find it later. For the second coefficient, it's just 1/2. It's done as well. The third one is not done. Notice that it is the previous 1/2 times a -1/2 and divided by 2 factorial. To finish that computation, I will need to take the 1/2 and multiply by -1/2, which gives me -1/4, and then divide by 2, which is the value of 2 factorial. This is going to give me a -1/8. What about the next one out? When I look at the next one, notice that these factors are the same, and inside of 3 factorial, there is a 2 factorial. That means that this part of the new formula is the -1/8. To get from here to the next one, I could multiply the -1/8 by -3/2 and divide by 3. The 3's would cancel, and -1/2 times -1/8 should give me a positive 1/16. Let's ring that in red so that we can find it later when we need to work on it. What about the final constant that we computed? Notice that up here, this is 1/2 times -1/2 times -3/2 divided by 3 factorial. The 3 factorial is a part of 4 factorial. It is 4, oops, I'm using the wrong color. It is 4 times 3 factorial. I can write 4 times 3 factorial. The first 3 factors and the 3 factorial will give me the value of 1/16. Then I simply need to multiply by -5/2 and divide by 4. When I get that, I should end up with, I believe, -5/128. Take a moment to see if you agree. Now that we have some coefficients, let's reread the problem to remember what it is we're supposed to be doing. It says find the binomial series for the function √1 plus x centered at 0. We have done that, though we haven't written out the polynomial into terms. We can do that next. After we're done, we're to approximate the square root of 1.24 to 3 decimal places. First, let's go ahead and write out some of the terms that we have gathered. Here are the constant coefficients that we have found. We have got the 1 for the 0th, 1/2 for the first. I've lost my 2 ringed in red, -1/8 for the second, 1/16 for the third, and the final was -5/128 for the fourth. Now what we want to do is put these into the format for the binomial series. Remember, from up above, when we put them into the binomial series, it is these coefficients that we found multiplied by x raised to that power. In this case, our power here should match the subscript, in this case k. The k here matches the power on x. Let's go ahead and write out our first 5 terms in this binomial expansion. Our first coefficient is 1. To write that out, this is going to give us the following. We're writing the expansion for 1 plus x to the 1/2 power, which is, of course, the square root of 1 plus x. This is going to give me a 1. It should be times x to the 0 since the k value is 0. The second coefficient we found was 1/2. That will be a 1/2 times x to the first, since the k value was 1. Next, we will have negative 1/8 times x squared, since the k value was 2. The third will be plus 1/16 x cubed, since the k value was 3. The fifth one will be minus 5 over 128 x to the fourth, since the k value was 4. The pattern continues from there. Our next job is to approximate the square root of 1.24. To approximate that, we need to be able to figure out what x should be. In other words, we're trying to approximate this decimal number using the formula up here. Notice that the formula has 1 plus x, but the number under my radical does not look like 1 plus x. So my first job is to rewrite the square root of 1.24 in a 1 plus format. This becomes 1 plus 0.24. That will give us the value for x. In other words, my x is not 1.24. My x is actually 0.24. Since x is going to be 0.24, that means that I will replace it in all of the terms above wherever x appears. Now, how can I get it to 3 decimal places of accuracy? It doesn't tell me which polynomial to use to approximate. If it said use the third, I would know that I would go out to the third. If it said use the fourth, I know I would go to the fourth. However, it didn't tell me. You'll know you have the right degree of accuracy when you add on another term and the first 3 decimal places do not change. That's how you know you have 3 decimal places of accuracy. Let me show you what I mean. Let's rewrite our polynomial down here in simplified form. The square root of 1 plus x is 1 plus 1/2 x minus 1/8 x squared plus 1/16 x cubed minus 5 over 128 x to the fourth plus ... It's possible I'll need more terms, but I won't know till I get started. The first thing I'm going to do is I'm going to look at what would be p sub 0. In other words, just use the first term. That's a 1. What would p1 be? In p1, remember, we'll take the first 2 terms, the original and then the first derivative part. If I plug in the 0.24 for x, then I need to compute what that value becomes. This becomes 1 plus 1/2 times 0.24. Let's take a moment to compute that, and then you can restart the video. You should have gotten 1.12. Now let's take a look at the next value out, which would be, P2. Which would be the sum of the first 3. Writing out the terms of P3, we have 1 plus 1/2 x minus 1/8 x squared. Plugging in the value for x as 0.24, I am basically only adding on again one more term, which means that when I compute this, I really only have to think about plugging in the 0.24 into the new term, negative 1/8 times x squared. If you take a moment, go ahead and compute it, then restart the video. Again, since the first 2 terms are the same, they're still 1.12. Computing the third term gave me 9 over 1250. Combining these 2 terms gave me the decimal expression 1.1128. Take a moment and let's compute the last ones that we have. You should be able to add on 2 more terms one at a time. Do that now and then restart the video to compare your answers to mine. I hope that you caught that I had a mistake up here where I wrote P3. It should instead be P2, since again, this is up to the second power. Now, when we look at this next one for P3, I got the value of 1.113. We are not yet at 3 decimal places of accuracy because the third decimal place is here is a 3 and up here it is a 2. If I rounded, it would be a 3, but if I rounded this one, it would go to 4. That is not 3 decimal places of accuracy. When I compute the next one, the fourth one, which is actually the fifth if you start counting at 0, I add on one additional term, the -5 divided by 128 times x raised to the fourth power. When I compute that, the new term subtracts 81 over 625,000. When I compute that one, I get this decimal number. This time, I have a 3 in the third decimal place in both cases. And in both cases, were I to round, I would round up. I would call that 3 decimal places of accuracy. So we can stop here. Let's take a look at the next example. In example 3, we are asked to find the first 4 terms of the binomial series for the function the cube root of 1 plus x, again centered at 0. We will then use it to approximate the cube root of 1.24. This time we're told how many terms to compute, and we're not asked to find a certain decimal place of accuracy. We will again assume that the series for this function does converge back to this function on its interval of convergence. Let's take a look then at this one. When we're looking at this, what we will do is first compute the first 4 terms by finding the p choose k. In order to find p choose k, we must have p. That means we need to rewrite the cube root into a power form, which would be the quantity 1 plus x raised to the 1/3 power. That means that our p, or power, is 1/3. Now we will compute the first 4 terms. The first term will always start with 0, which by definition will always give us the number 1. We get that one for free. The next one that we're going to look at would be 1/3 choose 1. For 1/3 choose 1, I start with the factor 1/3 since it is the top number, but I only need one factor in the numerator and a 1 factorial in the denominator. That makes this second coefficient 1/3. It's not terribly difficult. Let's take a look at the third coefficient coming from k equal to 2. This would be 1/3 choose 2. To compute that, I need 2 factors in the numerator, 1/3 and then 1/3 minus 1, which would be a -2/3. This will be divided by 2 factorial. Since 2 factorial is the number 2, we should end up with, I believe, and I hope, -1/9. The next one we need to compute would be 1/3 choose 3. To compute 1/3 choose 3, I will need 3 factors in the numerator and 3 factorial in the denominator. That will lead to 1/3 times a -2/3. And when I subtract 1 again from -2/3, I get -5/3. Then I'll divide by 3 factorial. Go ahead and take a moment to work that one out. When you multiply this one out, you should get a positive since you have 2 negatives. The 2 in the numerator here will cancel the 2 inside 3 factorial. That will leave us with 4 3's in the denominator, or 81, and only the 5 left for the numerator. This gives us 1, 2, 3, 4 coefficients for 4 different terms. Now we'll write the expansion for this binomial series using the first four terms. This will, of course, only be an approximation. This means that the cube root of 1 plus x is approximately equal to the first four terms. The 1 would be multiplied by x to the 0th power since k is 0, but that will just be a 1. The second coefficient 1/3 is multiplied by x to the first power since the k is 1. The third coefficient, negative 1/9, will be multiplied by x squared since the k value is 2. And the fourth coefficient, 5 divided by 81, will be multiplied by x cubed since the k value is 3. That's the first four terms of the binomial expansion. I can't say it's equal because it is an approximation as it is a finite polynomial, not the infinite one that you would get if you did the full series, since the power 1/3 is not a whole number. Our second job is to use that to approximate the cube root of 1.24. If we're going to approximate the cube root of 1.24, we again need to write it in the binomial expansion form, which is to write it as the cube root of 1 plus 0.24. That means that our x is again 0.24, not 1.24. This means that we will replace the x in our four terms with 0.24. Go ahead and pause the video, work it out, and turn it on to compare your answer. After plugging in 0.24 and doing the calculations, I got an approximate value for the cube root of 1.24 as 1.074453 repeating. Just for fun, I plugged the cube root of 1.24 into my calculator to see how this compared. I got a value of 1.074337071 with a continuing number of decimals after that. You'll notice that these agree at least up to 3 decimal places of accuracy. And in fact, this is pretty amazing considering that I only used 4 terms from this binomial series to do it. I got a very accurate answer with only 4 terms, and it was a polynomial to boot. What could be better? Let's move on now to our next example. In the final example for this video, we want to take a look at the binomial series for 1 plus x to the negative 3 centered at 0. We will again assume that the power series generated by that function converges to that function on its interval of convergence. Then we're going to use it to approximate 1 over 1.331, which is another way of writing 1 over 1.1 cubed. When we do this, you need to keep in mind, of course, that the function equal to 1 plus x to the negative 3 power could be written in the form of 1 divided by 1 plus x quantity cubed. Now hopefully you can see the connection between what we're supposed to find after we find the first 4 terms and this particular format for the function. Let's find the first 4 terms by determining first off what the value of p is. The value of p cannot come from the rational function form. It must come from the binomial power form, which tells us that p must be a negative 3. The first 4 terms then will be negative 3, choose 0, choose 1, choose 2, and choose 3. We will compute the 4 individually, then turn the video back on to see if your answer matches mine. Let's see if your answers match mine. Remember that whenever the k value is 0, we define that coefficient to be 1. Negative 3, choose 1 should be negative 3. Negative 3 choose 2 should be 6, and negative 3 choose 3 should be negative 10. Notice that these are alternating in sign because our p-value was negative. Now write that as an expansion going only up to the fourth term. It won't be exactly equal because we're not using the infinite polynomial, but it is an approximation. Each one individually, each coefficient, is multiplied by x raised to the same power that they had as the bottom number. That would be x to the 0 for the first coefficient, and x to the first for the second, x squared for the third, and x to the third for the fourth. Again, it depends on how you want to count them. If you want to call these first, second, third, and fourth, or if you want to call these zeroth, first, second, and third. It's purely a matter of semantics and a sort of personal choice. What is our next step? Our next step is to use this to approximate 1 over 1.331, which is 1 over 1.1 cubed. To approximate 1 over 1.1 cubed, I need to figure out how to get that written in the same format as the function I have the approximation for. I need to rewrite the 1.1 cubed then as 1 divided by the quantity 1 plus 0.1 quantity cubed, since 1 plus 0.1 is 1.1. That, however, implies that x, instead of being 1.1, is in fact 0.1. Now I can get an approximation for that by plugging in the value 0.1 in place of x in my 4-term polynomial approximation. Take a moment to compute the numbers, then turn the video back on to see if your answer matches mine. Hopefully, when you plug those in, you got the same value that I did, that our approximation is exactly 3/4 or 0.75. For fun again, I went ahead and put it into the calculator to see what my calculator thought the value of 1 divided by 1.1 cubed was. For this, I got an exact value of 1,000 divided by 1,331, or in decimal notation, 0.7513148. Notice that these do agree up to 2 decimal places, and even if I were to round this, I would still have the same value. I don't have 3 decimal places of accuracy, but I do have 2. I feel sure that if I went out perhaps 1 or 2 more terms, I could easily get 3 decimal places of accuracy. I hope that you've enjoyed learning about Pascal's triangle and how it can be used to expand binomials raised to whole number powers, and also that you've enjoyed learning about binomial series and how you can expand binomials raised to powers which are not whole numbers by using the special formula to compute the coefficients, and how you can use this to approximate different values to a high degree of accuracy with only finite polynomials. This is the end of this video.